All right, let's find the binding energy and the binding energy per nucleon of chromium-52. This is my 5th binding energy video in the space of 20 minutes here, so I'm getting a little crazy, crazy. All right, so chromium means that it's got 24 protons, right? So we're going to take chromium-52 and represent that with 24 protons and 24 electrons, right? And then how many neutrons here? Okay, let's see, where is it? 52 is right here. Here's our mass, right? Okay, so chromium-52 is a mass of 51.940512 U. Okay, now how many neutrons is it? Well, it's 52 minus 24, right? Okay. Embarrassingly, my brain is just so fried here, wigged out that I'm using my calculator. That's 28. So there's 28 neutrons. Okay, plus 28 neutrons. And the tendency here is that as we go up in atomic number, that we start to get more and more neutrons per proton, right? The lower ones that we did so far had even numbers of protons and neutrons. They were the same. Notice that now we have more, right? And there isn't even a stable isotope of chromium, if you notice, that has the same number of protons as neutrons. This one here would have 26 of them, right? Okay. And that is a pattern. Notice that the stable nuclei here, 3 out of the 4 have even numbers of protons, right? So anyway, there you have it. By the way, most of it is chromium-52. Oh, this is interesting. Here's one with both odd numbers, right? And that's the predominant one. So that's unusual. Okay, so nuclear stability. So let's look at this. Let's make this thing up. I'm going to make these guys up by using a neutral hydrogen atom, right? Which is also in your little table of nuclei. So I'm going to say 24 of these because this takes into account a proton and an electron, plus 28 free neutrons. Right now, the mass of a free neutron is more than the mass of a bound neutron, because you'd have to put in energy to free it from the nucleus, and that putting energy into something would give it mass. Okay, if you pitch a baseball, the baseball has more mass when it's moving than when it's sitting still. Anytime you give in, if you lift a mass up, if I lift a 1 kilogram mass in the front of my room, it gains mass. Just wrap your mind around that. Not much, but it does. It has to. Okay. It's getting spicy. All right. So let's figure this out. So 24 times 1.007825 plus 28 times 1.008665. And I'm getting on this side a whopping 52.430420 U's. Okay, and I'm writing that 0 there because it exists and it is 0. We know it. All right, and then on this side we got 51.940512. And so I'm going to subtract this from this and get the mass defect. Okay, so minus 51.940512. And the term defect sounds like it's, there's something wrong. And that's based on the old concept that mass is conserved, which it's not. Mass and energy are conserved. Okay, so 0.489908. That's how much mass these parts gain when you tear them apart and you put them a long distance from each other, right? So that means that you'd have to put this much energy. You have to put that much energy per atomic mass unit in to tear it apart. So let's multiply by 931.5. If you panic on this test, right, and you're like, God, I don't remember how to do this problem. Here's what you do. Find the mass of everything on the left side and the mass of everything on the right side. Yeah, subtract, multiply by 931.5, and do it confidently. All right, so here we have 4 sig figs. Here, this legitimately we have 6 sig figs, right? But here we have only 4. So this is our binding energy, right? And then this is our Be, right? And then we want to also know the Bepen. And the reason we do binding energy per nucleon is it gives us a way to compare one nucleus to the other, how, the relative stability of it. Large nuclei, by their default, even unstable large nuclei, have tremendous binding energies because there's so many particles, and by the time you tear every last thing out of there, you've done a lot of work. But if you do it per nucleon, it's kind of like gross income per capita, right? Sort of thing, right? That only there are no Bill Gates in the atomic world. All right, so let's divide by 52, that's the number of nucleons. That's what 52 means, is total things, right? So divide by 52, and I've got 8.775948. Now we only have 4 sig figs, so 1, 2, 3, 4. So I'd have to say 8.776. And that's MeV per nucleon. All right.